Good morning, Algebra 2 CP students. Hopefully, you're having a great day so far. Today, what I'd like to do is continue our discussion on graphing quadratic functions in vertex form by showing you a bunch of examples as to how that's actually done. Yesterday, I went through kind of a lengthy discussion, but a necessary discussion to talk about the transformations that exist when you're dealing with vertex form. Vertex form of a quadratic function is given by f of x equals a times x minus h squared plus k. A, h, and k are all constants that represent transformations, or methods through which the parabola is moved or changed compared to the parent function of just x squared. K represents the vertical shift, which moves your parabola up or down. H represents your horizontal shift, which moves the parabola left and right. We talked about kind of a weird negative thing that happens with H because there's a minus H in the formula. If you see x plus 1, that means it would have originated from x minus negative 1, so H would be negative 1 here. It's almost the opposite. You can think of it that way. And together, the horizontal shift and vertical shift give us the vertex. We could say that the vertex is h comma k. Once we have the vertex, we can go ahead and plug in some points to find the rest of the parabola and figure out the shape of it. But we can also get some mental confirmation as to what the shape of the parabola should be based on the stretch. We figured out that if the stretch is equal to 1, then it would have the same stretch as the parent function, increase at the same rate. If the stretch is greater than 1, then it would be increasing at a faster rate, meaning it would be taller and skinnier. If the stretch is a fraction between 0 and 1, it would be increasing at a slower rate because it would be wider and fatter. And if a is negative, it's flipped upside down or reflected about the x-axis, although all of the other things change. If it's a fraction, negative fraction, between 0 and negative 1, then it would be wider, just upside down instead. And if it were a negative number less than negative 1, well, then it would be really, really steep, but still going down. Okay, so we use that information plus our plugging in of points to find out what the rest of the parabola should look like. As we did yesterday, we really only have to plug in 1/2 of the parabola because we know it's symmetrical, and we can just reflect those points over there. What we talked about on Monday but didn't talk about yesterday was domain, range, axis of symmetry, maximum minimum value, and end behavior. So in the 4 examples that I have prepared for you today, I will make sure to go through that information with you. All right, with that introduction out of the way, let's go ahead and get into some examples. Let's do it. You ready? Let's start with this first example here. Just some classic graphing quadratic functions in vertex form. If I had f of x is equal to x minus 3 squared plus 1, right? Again, remember that our general form is f of x equals a times x minus h squared plus k. And so we're able to identify what values serve as our a, h, and k here to help with finding my vertex. Again, step 1 is to always find that vertex. Remember, the vertex is given by h comma k, which in this case would be, let's see, it looks like h would be 3 because you see x minus 3 would fit in for x minus h. So h would be 3, and k would be positive 1. So your vertex would be at the point 3 comma 1. You could also think of this as, in case that negative h kind of confuses you, I always like to say, when I'm faced with an example, what value for x makes this middle piece equal to 0? And the value for x that would make it 0 is 3, so therefore our horizontal shift is 3. Okay, because 3 minus 3 would be 0. So what I would do on my coordinate plane here is, I'll show you, I would go ahead and start at the point of 3 comma 1. 3 comma 1 is, let's see, 1, 2, 3 comma 1. It's right here. Let me use a different color so it's nice and clear. 3 comma 1 right there. That's our vertex. Now that I know where my vertex is, I can go ahead and create a table of values to find out some more information about that parabola. Here's x. Here's my function, x minus 3 squared plus 1. Before we actually plug in some points, though, we can actually, get a little bit of a mental picture by using the stretch. We know that the stretch here is equal to 1, right? There's like an invisible positive 1 out there. So the fact that the stretch is equal to 1 means it should be upwards facing, as opposed to downwards. It's a positive number. And it should be increasing at the same rate as the parent function. So it shouldn't be particularly narrow and skinny or particularly wide and fat. It should be just a regular old parabola. So let's take a look. I know that my vertex is at the point 3, comma 1. And since I know my x-coordinate of the vertex is at 3, let's plug in a couple of points to the left, a couple of points to the right, just to see what this parabola looks like. I'll plug in 2 and 1, as well as 4 and 5. Just counting on the x-axis to see if we can plug in some other points. There's no mathematical rule or law, by the way, that states we have to do 2 to the left and have to do 2 to the right, but I think that's a fair number of points for us to be able to get an accurate picture. I think 1 is not quite enough, and I think by the time you get to 3, it gets to be a little overkill. So I think 2 is kind of like that nice happy medium. All right. So in any case, since we know a parabola is symmetrical, what we can do now is just pick one of the sides, plug in some points, sketch half the parabola, and then just mirror over to the other side. So let's do it. If I picked 1 and 2, you could certainly do that if you want, but I'll pick 4 and 5 just to show you and make it a little bit more challenging. If I take 4 and plug it in for x, we would get 4 minus 3 is 1. 1 squared is equal to 1. Plus 1 would make 2. So that would mean that since I plugged in 4 and I got 2, then the point of 4, comma 2 would exist on the graph. All right. If I took 5 and plugged it in for x, I would get 5 minus 3 is 2. 2 squared is 4. 4 plus 1 is 5. And so therefore, because we plugged in 5 for x and got 5 for y, the point 5, comma 5 would exist on the graph. And you already start to see half of that parabola shape forming here, which is a good sign. So now we can just go ahead and reflect everything over to the other side. If this was 4, comma 2, this one also has to be a y value of 2. If this had a y value of 5, this also has to have a y value of 5. Visually, you could see that this point has to have a mirror image point here. This point has to have a mirror image point here. And that's because any parabola is symmetrical. And you can now go ahead and connect them all together. All right. Instead of plugging in 4 and 5 for your x coordinates, you could certainly opt to plug in 1 and 2 if you want, and then flip those values down here. Totally fine. You would just sketch the left half of the parabola first, and then flip over to the right due to symmetry. All right. So let's talk about our characteristics real fast. Domain. Remember, the domain refers to how far to the left does the parabola go, how far to the right does the parabola go, what space does it occupy on the graph with respect to the x-axis. Well, it goes forever to the left and goes forever to the right, so we'd be able to say that our domain here is all real numbers. Our range is not all real numbers, though. The graph does not go down forever. The lowest it goes is positive 1. But it does go up forever, so I would say that my range is 1 to infinity. Let's go into now my axis of symmetry. Again, the axis of symmetry is sort of this invisible vertical line that's going to cut the parabola in half. So if you notice, this line right here is cutting the parabola in half, and that line is given by the equation x equals 3, right? Because it goes through 3 on the x-axis. So we'd be able to say that the axis of symmetry here is x equals 3. Your maximum and minimum value, or I should say maximum or minimum value. A parabola cannot have both a maximum and a minimum at the same time. It either has a biggest point or a lowest point. In this particular case, it has a lowest point, and that lowest point occurs right here at positive 1. We'd say it has a minimum at f of x equals 1. At f of x equals 1, not a maximum. And lastly, the end behavior. I would say here, let's see, as x approaches negative infinity means as we trend to the left, as we move to the left of the graph goes up, right? As our x coordinates get smaller, as our x values decrease, our y values increase. So as x approaches negative infinity, f of x approaches positive infinity. And same thing on the other side. As x approaches positive infinity now, as our x values increase, the function also continues to increase. And that would be a complete graph of something in vertex form with information. All right? Hopefully that makes sense. I know that was kind of a long explanation, and you might be thinking, holy cow, does it take that long to graph one of these things? But no, it doesn't. I was just trying to go very slow and explain it to you. Let's go through the next one a little quicker. Ready? What if I had something like this? F of x is equal to negative 2 times x plus 4 squared plus 5. All right, next example. Drawing my coordinate plane first so I can go ahead and start labeling things as they become important here. So right away, before we actually do any math, we could actually get a visual for what this parabola should look like. The fact that the stretch is negative 2 means that the parabola should be facing upside down, like an N shape, and it would be going down pretty quickly, right? Twice the rate that the parent function normally increases, this would be going down at that speed. So that's just like a mental image of what it should look like. It should look like a steeper N shape. We could also find the vertex right away by saying, well, the vertex is h comma k. In this particular case, it would be negative 4 comma 5. Because negative 4 would make this middle piece equal to 0. It's the opposite of this. And 5 translates directly. That's our h and k. All right, so we know our vertex is negative 4 comma 5, negative 1, 2, 3, 4, comma 1, 2, 3, 4, 5 right here. Since we know that our x-coordinate of the vertex is at negative 4, we should be able to create a table of values and figure out some more information. So we have negative 2 times x plus 4 squared plus 5. Our vertex is right here in the center. Let's do 2 values to the left and 2 values to the right. Since my x-coordinate of the vertex is negative 4, I could plug in negative 6 and negative 5 from the left, right, if we continue in the negative direction. Or I can plug in negative 3 and negative 2 from the right if we continue in this direction. It's just counting from the x-coordinate of the vertex. 2 to the left and 2 to the right. Think of a number line. All right? So we could pick whichever side we wanted to. In this case, I'll pick these numbers here, take them, plug them in, see what they come out to be, and then reflect to the other side. Ready? If negative 3 goes in, we would do negative 3 plus 4, which is 1. 1 squared is 1. Times negative 2, 1 times negative 2 is negative 2. Plus 5 is positive 3. And so therefore, my next point would be located at negative 3 comma 3. That would be right here. After that, we plug in negative 2. Negative 2 goes in. Negative 2 plus 4 is 2. 2 squared is 4. Times negative 2 is negative 8. Plus 5 is negative 3. So my last point would be at 2 comma negative 1, 2, 3 right here. We see this half of the parabola starting to take shape, right? You kind of see that? And so we can then just reflect over to the other half. This has to have a mirror image point here because the vertex is the center and my parabola is symmetrical. This has to have a mirror image point here because my parabola is symmetrical. And then we just continue our graph. And again, you can fill in your table of values to say, well, if this is 3, then this has to be 3. If this was negative 3, this has to be negative 3. All right? Hopefully that makes sense. Just very quickly running through the characteristics. See, it doesn't take that long. It doesn't take as long as that one. Domain would be all real numbers. It extends to the left and right forever. Range, I will write, is negative infinity to, let's see, 1, 2, 3, 4, 5. It's the highest it goes, right? How far down does the graph go? It goes down forever. How far up does the graph go? It goes up to 5. Your axis of symmetry here is, again, the vertical line that cuts the graph in half. It would be right here. It's x equals negative 4. Something kind of neat to note is that the axis of symmetry is always the same as the x-coordinate of the vertex because the vertex is that center point. So that's what's going to cut it in half. I might as well write in the domain if I'm going to write in all of these. I was only going to write in a couple, and then I was like, I might as well write them all in. All real numbers. The maximum or minimum. This value, this parabola in particular, has a maximum value. So we'd say it has a maximum at, what's the highest that it ever goes? Looks like it goes up to 5. I'd say the maximum is at f of x equals 5. Notice that kind of matches the y-coordinate of the vertex, because that controls how up, high, or low it goes, right? It's all like making sense, all connected. And lastly, the end behavior. I would say, let's see, as x approaches negative infinity, as we continue to the left, as your x values decrease, what happens to your function? What's your function expected to do? It's also expected to decrease because there's a downwards facing arrow on that left-hand side. On the right-hand side, as x approaches positive infinity, the graph is also going down. There's a downwards facing arrow. F of x approaches negative infinity. All right, and so that's how you would sketch a graph of that with all of this relevant information as well. I originally had 4 examples prepared for you today, but I think we could just get away with doing one more. I don't want to keep you here for too long, but hopefully that makes sense. Let's do one more example, and then we should be good to go for the day. All right. Ready? Last one. Let's do. Because I think the other examples shows off something that we kind of already saw, another negative example. How about a fraction for the stretch? F of x equals 1/2 times x plus 1 squared minus 3. All right, let's take a look at something like that. Well, again, it's in vertex form, so I would start out by finding the vertex. Here, h would be -1. It's the opposite of that. K would be -3. And so our vertex is -1, -3. Additionally, the stretch being 1/2 tells us that this is an upwards facing parabola, but it is going to be wider and increasing slower than normal because it's less than 1, right? 1 is what the parent function is. It's only increasing at half the rate, so it's going to be a little bit wider. All right, so we already kind of have a mental image of what this should look like. Let's confirm that in our head. Or let's confirm that mental image that we created in our head on paper. All right, now we can go ahead and create a table of values. Table of values. Table of values. We have x. We have our 1/2 times x plus 1 squared minus 3. Our x-coordinate of the vertex is -1. That resulted in a y value of -3. Let's plug in a couple values to the left and a couple values to the right. To the left, we have -3 and -2. To the right, we have 0 and 1. Just think of it like a number line. I know what this is, so let's find out what this is and what this is, as well as what this is and what this is. All right. Personally, I would elect to plug in 0 and 1. I think those numbers are going to be easier to work with, so let's see what happens. 0 goes in. I would get 0 plus 1 is 1. 1 squared is 1. Half of 1 is 1/2. Don't be afraid of the fractions. 0.5 minus 3 is -2.5, or -2.5 if you prefer. You could also say it's -5/2. Okay, so my next point would be at 0, -2.5. Should be right about there. Don't be afraid of the fractions. That's definitely doable. 1 goes in. We would get 1 plus 1 is 2. 2 squared is 4. Half of 4 is 2, integers this time. Minus 3 is -1. So our last point would be at 1, -1 right here. Again, we know that our parabola is symmetrical. We see half of it starting to take shape here. That means the other half would be here and here. Right? This would therefore be -2.5 and -1. And we're able to sketch our parabola just like this. There we go. Nice, pretty looking parabola. All right. Very quickly, I'll go through the characteristics one last time. Hopefully it makes sense how we sketched it. Do you see how fast it is once you understand how to find the vertex, how to plug in points, and how to reflect? That's really all there is to it. I don't want to overcomplicate it, but I did want to show you all that transformation stuff because it's important to understand why this works the way it does, because these types of patterns, the vertical shift, the horizontal shift, the stretch, that shows up in a whole bunch of different graphs, some of which we're going to do later in the year. But anyway, let's keep going. We have our domain. Notice this parabola is extending forever to the left and forever to the right. It would therefore have a domain of all real numbers. You might be asking yourself, does a parabola always have a domain of all real numbers? Something to think about. How about the range? Let's see. How far down does it go? It goes down to -3 inclusive, so I'm going to use a square bracket, and it goes up forever, infinity. The axis of symmetry is the same as the x-coordinate of the vertex, but it's really the horizontal line that cuts the graph in half. That happens to exist right here. See how it just slices that graph directly in half? We'd say that's at x equals -1. The maximum or minimum value. In this case, the parabola has a minimum value, and that minimum occurs at f of x equals -3. The lowest value the function could ever produce or output is -3. And lastly, the end behavior. We'd start with two parts. As x approaches -infinity means as x continues to the left, as our x values get smaller, our y values, notice, will continue to get larger and larger and larger. We'd say f of x approaches infinity. And likewise, as x approaches positive infinity, same thing. We have another up arrow over here, so we would say f of x also approaches positive infinity. All right? So there we go. That's exactly what you'll be expected to do on any sort of assessment. We will have a couple of practice days on this later this week. We do have another graphing form to go over. That's graphing in standard form, and then we'll have our next progress assessment and go from there. I want to thank you for your attention and focus today. Hopefully that was helpful. Try to go through those examples again if you need to. The other example, I guess the fourth one I was prepared for today, was f of x equals the opposite of x minus 4 squared plus 1. So see if you could try that one on your own. I think it's an interesting example. You could always use something like Desmos to check your work. You could plug in the graph that you got, type it in, see if that picture that's generated matches the picture that you came up with, or you could use a graphing calculator if you have access to one. Thank you so much again for your attention today. I hope you have a great rest of your day, and good luck. Take care, everyone.